Hello everyone, my name is Xiaohan Wei. I'm currently a research scientist at Facebook. Today I'll give a talk titled Online Primal Dual Mirror Descent Under Stochastic Constraints. This is joint work with Hao Yu from Amazon and Michael J. Neely from USC. Let's recall what online convex optimization is. So OCO is a multi-round process of making decisions without knowing what to optimize. So namely, at each time solved, one has to choose a decision variable from decision set X before observing what the actual loss function is. These loss functions can be arbitrarily time varying, and they might not have a fixed predefined distribution function. Our goal is to minimize the following regret, which is loss between a proposed algorithm and an optimal fixed decision in hindsight. Note that here we are comparing to a fixed decision instead of a time varying one. This makes the OCO a tractable objective. A general algorithm solving this problem is called online mirror descent. So it works by defining a regularization function R, which is smooth and strongly convex with respect to some predefined norm on X. Then we define a Bregman divergence, which is a second-order residual of the Taylor expansion of this regularization function. Then at each time solve, we choose a decision variable via this mirror descent update with a gradient vector from the loss function in the last time slot. And then assuming this optimization is easy to do, and under proper choices of the learning rate, one can show that OMD achieves square root T regret. This square root T regret contains a dimension factor B, which changes according to different scenarios. For example, in Euclidean spaces, where the Bregman divergence is just the regular L2 norm square, we get the polynomial dependency on the dimension, whereas in the probability simplex case, we get log D dependency. So OMD works pretty well when the mirror descent step is easy to solve. What if we have a rather complicated decision set? For example, the decision set can be time varying. It can even be characterized by a sequence of stochastic functions. Furthermore, in many scenarios, the realizations of the stochastic functions might not be observed before making decisions. This makes a vanilla OMD not applicable, and furthermore, it makes enforcing this constraint over each time slot intractable. So instead of enforcing these constraints per time slot, instead we aim at the following more relaxed goal. So we aim at minimizing the aforementioned regret, and at the same time, we allow this decision variable to violate the constraint but keep the overall long-term violation small. So the previous works solving this problem is called Primal dual gradient descent. It has different variations in many existing works. Basically, this method works in Euclidean spaces, and under strong Slater condition, where there exists a decision variable that lives in the strict interior of the decision set, one can get polynomial D square root T regret and constraint violations simultaneously. And when one does not assume Slater condition, we get somewhat worse regret and constraint violations there is a trade-off parameter which trades the regret with the constraints. So in this work, we propose a new online primal dual mirror descent algorithm. The analysis of this algorithm relaxes the Slater condition as mentioned before, and in particular, it allows equality constraints. Furthermore, it works in general non-Euclidean spaces. It recovers the polynomial D dimension dependency in Euclidean spaces, and it gives even better log D dependency in probability simplex cases. So let's start by describing what our algorithm is. So we define an augmented gradient vector, which is a weighted version of the objective gradient and constraint gradients. The weights are characterized by a Lagrange multiplier, which will be updated later. At each time slot, we solve an online mirror descent problem as we had before. But this time, it's only over a very simple decision set instead of a complicated one. And then after that, we update a Lagrange multiplier via proximal step. It's worth mentioning that for our algorithm to work in probability simplex case, we have to do an extra probability mixing at the end of each time step. The reason for this is technical, and it is likely this step can be removed by better analysis, which we don't know yet. Our main assumption making this algorithm work without Slater's condition is the following, called sequential existence of the Lagrange multiplier, also known as a cell. So simply put, it asserts that for any, assume for simplicity that square root t is an integer, it asserts that for any square root t interval on the horizon, we can define a Lagrange dual function, and then we have to make this Lagrange dual function, we have to assert that this dual function, the set of maximal of this dual function is non-empty and bounded. In particular, the aforementioned strong Slater condition actually implies the Selm condition. And when the constraints are all linear equalities, the linear independence of the support vectors of these constraint hyperplanes actually implies the Selm. So this makes such an assumption more relaxed compared to the strong Slater condition used in previous works. So under such a condition, we have the following theorem. We can choose the proper trade-off parameters and get polynomial D dependency with square root T regret constraint violations in the Euclidean spaces. And furthermore, when the decision set is a probability simplex and we choose a proper mixing variable, we can get log D regret. Log D dimension dependency and square root T regret as well. Let's take a look at the simulation on a job scheduling problem in data centers with pacing constraints. So we have 5 server clusters, and they contain in total 50 servers. So in architecture illustrations like this, we have a simple, we have a single sequence of jobs arriving at the router, and this router will route these jobs to different server clusters. according to certain rules. And these server clusters lives on different geographic locations. We assume that electricity prices on these geographic locations vary across zones and time. Here is a figure illustration of the electricity price varying per 5 minutes. You can see that the price actually varies very abruptly. We assume the job arrival process is a Poisson. And furthermore, to prevent the router from routing jobs consistently to one single cluster to overload it, we have additional resource consumption criteria. Basically, it penalizes the router. When it tries to schedule more jobs to a single cluster. We use HIT as a unit to denote the unit of resource consumptions per unit power allocations to a single cluster or single server. Finally, we have a job service rate on each server, which goes according to a Pareto distribution. We denote xt as a set of decision variables, which is a power allocation variables to different servers. They can be chosen in an interval between xmin and xmax. So the problem we aim to solve here is the following. We aim at minimizing the electricity budget spend over T time slot, subject to the average service rate is bigger than the average job arrival rate. Furthermore, we have this pacing constraint, which says that the resource consumption on each cluster has to be a fixed proportion on average compared to the total resource consumptions over all clusters. These beta 1 and beta 5 to beta 5 are no constant ratios, and they sum to 1. Here is the experimental results we plot. So we are comparing to best fixed strategy by knowing all the electricity price over T time slots, as well as all the job arrivals and the pacing resource consumptions. In such a case, it only needs to solve a static optimization problem in order to get the best decision variable. It's fixed. And then we are comparing to another algorithm called React. Basically, it tries as best as it can to balance to adjust the service rate to meet the arrival rate and to keep the budget pacing as good as possible. So one can show that we can see that in these figures, our algorithm achieves better electricity money spent compared to proposed method and compared to the best fixed strategy and the React algorithm. At the same time, it also approximately satisfies the time average job service constraint, and the budget pacing constraint violation is also very low. So that's it. Thank you.